Welcome back. Today we're going to talk about vertical kinematics and gravity. Today the things we're going to be learning about are the vertical adjustments to the kinematic equations, the acceleration to gravity, and solving practical problems using vertical kinematic equations. When it comes to gravity, typically the variable we're going to use for this is just simply g. Whenever you see this lower small g right up here, that's telling us that we're going to be dealing with gravity. All objects fall or accelerate at the same rate, and that's g. That rate is 9.8 meters per second squared. Um, Notice meters per second squared right here. All right, gravity, this is the units for acceleration, so gravity is an acceleration. Um, Gravity, again, I'm going to tell you, is an acceleration. It's just a specific acceleration. You guys have solved for several accelerations that we had to find, and what we want to know then, or say then, is gravity is always going to be 9.8 meters per second squared. In ICP, we simply used an easy number like 10, but now we're going to start getting more specific with it. All of our horizontal equations get changed into vertical kinematic equations by changing A to G, because it's gravity that's pulling on the objects now. It's not just an unknown acceleration, it's G. So you could think of these as being easier because you're always going to know what G is. A lot of times when it came to the horizontal, you had to solve for A. And gravity is different on different planets. So different planets are going to have different values for G. Okay, the vertical changes, you can see here in our first equation that we've gone from A to a G. We've put a G in here, but the equation still stays the same. This equation is all the same, except now we've gone to a G and we've changed it from XF and XI to YF and YI. The nice thing is still the YI a lot of times is going to go to 0, so this part of the equation will go away. We won't have that part there. It'll just be YF at the end. And then down here, instead of XF equals XI plus VIT plus 1 half AT squared, it's become YF and YI, and G has replaced the A here. So it's the same four equations, and we haven't done anything different to this one. It's the same four equations, except now we've replaced A with G, and the X's become Y's, because now we're dealing with things that are typically falling or things that are slowing down because gravity is pulling on them. That's the main thing here. They're either falling or slowing down because of gravity. All right, example. A football is kicked straight up into the air with an initial velocity of 35 meters per second. The football is kicked at a height of 1 meter. So let's first of all make our little list here. The stuff that they're giving us here. What information are they giving us from the problem? Well, they tell us that the initial velocity is 35 meters per second. It's kicked from a height, so that's yi is 1 meter. And then we obviously know that gravity is 9.8 meters per second squared. Okay, in this first problem here, then they're adding to that t equals 1 second. So now they just gave us time. They want to know how high it is, and they're giving us time. Remember, the other day we said that if we weren't given time, this right here was the equation we wanted to use. All right, the VF squared equals VI squared. But now they're giving us time. And if I want to know the height, this becomes very easy. YF a lot of times is the height. All right, in our equations, in our problems, they're going to use the word height, but YF is what the height is. All right, so again, a lot of times YF is the final height that it is. All right, they're going to use an H there, final height. In this case, they do give us an initial height, and that becomes YI. So this would be final height, YI is initial height. So I'm going to use this equation. YF equals YI plus VIT plus 1 half GT squared. And now it's just a matter of starting to plug stuff in. The initial height, they tell us, is 1 meter. The initial velocity is 35 meters per second. The time is 1 second plus 1 half. Here's the other thing. Gravity we're going to use is negative 9.8 because gravity acts down. We hadn't really talked about that yet. This should be a negative 9.8. And then t squared, that's 1 squared. Okay, I went ahead and punched the numbers in here, and what you get then It's a height of 31.1 meters. Um, on to the next one. How long till it is at 3 meters? Well, again here now, they're wanting time. How long here is until? That there means time. So I'm going to pick an equation that has time. If I go back to these equations right here, um, all right, my eraser's not working here. If I go back to these equations right here, the top one's got time, but it doesn't have any y's in it, so I can't find height. The second equation has y's, but it doesn't have any time in it. So I'm going to have to go to my third equation here, all right, because it's wanting to know how long, which means the time, until it's a certain height. So my equation then becomes, again, yf equals yi plus vit plus 1/2 gt squared. This time, they're telling me that I don't have my time anymore. This is a different problem, but they are telling me that yf is going to be 3 meters. So I can plug it into the equation now. I get 3, yi is 1, plus 35 t plus 1/2 gt, or not g anymore, sorry, that's negative 9.8 t squared. Now I've went ahead and plugged this into um, my little app I have on my iPhone here, and we get 3 equals 1 plus 35, and I don't like to use this t because sometimes apps and computers don't understand t, so I'll put x plus negative 4.9 x, and some of you may, how do I do this squared? Well, there's a little upside down caret button like this, and when I do that, and actually I just found out my little app didn't like the plus and the minus here, so I had to get rid of the plus, and when I do that, then I'm going to get an answer of x, or rather t, because x was in for t, and I get a time of 7.08 seconds. Now, I'm not really liking this answer. I'm going to have to double check. Okay, that is one of the times. The other time is going to be 0.06 seconds. So it's going to be at 3 meters at two different times. It's going to be there on the way going up at 0.06 seconds. And then when it comes back down, it's going to be 7.08 seconds before it gets back down to 3 meters. Alright, let's look at another one here. A model rocket is launched straight upward with an initial speed of 50 meters per second. It accelerates with a constant upward acceleration of 2 meters per second squared until the engine stops in 3 seconds. What is the maximum height reached by the rocket when the engine stops? Well, let's make our list of information here. Alright, has an initial speed 50 meters per second. Has an acceleration of 2 meters per second squared. And it has a time of 3 seconds. What is the maximum height? That's my YF. So as I look at my equations, the equations we have, this top one doesn't have a YF. This one does, but it never has time, and it asks me at a certain time. So now we're talking about, again, this equation here. So I want to find YF. I can say if it's a rocket, common sense tells me that yi is 0 meters per second squared. So we're going to have yf equals yi plus vit plus 1/2, I'm going to leave a little space there, t squared. In our other problems, we were using g because gravity was, the objects were falling, or it was gravity that was slowing them down. In this case, we don't have, their object's not falling, and gravity's not slowing it down. And in actually contrast, this rocket is being accelerated by the engine. So it's telling us the acceleration is not g, it's actually a, or 2 meters per second squared. So if I put my information in here now, I can find yf. yi goes to 0, so I'm not even going to put it in here. vi is 50 times 3 plus 1/2 times 2 times 3 squared. What we get here for an answer then is this rocket is 159 meters off the ground in 3 seconds when the engine stops. Well, hey, I hope this has been beneficial. I'll catch you on the flip side.